Okay, morning everybody. We're moving on to chapter 7 now. So the second one on polynomial congruences. So in chapter 6 we've looked at linear congruences, polynomial congruences of degree 1. And we also looked at the Chinese remainder theorem, which we presented first as a means of solving simultaneous congruences. Given a specified set of congruence classes, as long as the different moduli are co-prime, any set of congruence classes for different moduli which are pairwise co-prime, there will always exist a unique congruence class modulo the product of all the moduli that represents each of these congruence classes. And that's going to be an important tool that we're going to use in the later part of this chapter 7. Okay? So we're aiming for a method or an algorithm to solve the general problem, which is fx congruent to 0 modulo n. Okay, where f is a polynomial with integer coefficients as well. Now the method is going to be kind of like a number of different elements to it. Okay? The overall method will be based on, so you recognize this, based on the prime factorization of the modulus. Okay, so the modulus is going to factor into products of primes. So this is the pi distinct primes. And the solutions to we're going to solve each polynomial modulo each of the different prime powers. Okay, so the original problem will be to solve a certain polynomial congruence modulo some general modulus. But in order to do that, we're first going to solve a system of simultaneous congruences. Okay? So now you have one of these congruences for each of the distinct prime factors of your n. Okay? So n is various prime factors. They each occur to various powers. And what we're going to do is we're going to solve each of these subproblems. So the method will be based on the prime factorization of n and the solutions to these. And each set of solutions, so you'll have x congruent to bi modulo bi to the ai. Now, when I say each set, I'm talking about the fact that each of these congruences might have multiple solutions, many solutions. But for a choice of one solution for each I, you have a system like this. You have the specification of one congruence class modulo pi to the ai for each value of I, and this is something that we're going to apply the Chinese remainder theorem to lift to a overall solution modulo n. Each set of solutions here will lift via the CRT. Maybe lift isn't a great word, but we're going to use lift in another context, but let's just say correspond via the CRT to a solution x congruent to some beta modulo n of the original problem, f of x congruent to 0 and 1. So now we'll examine all these different parts in detail. In particular, how to solve these ones. Actually, this is where we talk about lifting. How to solve these kinds of problems. Polynomial congruence congruent to 0 modulo a power of a prime. But once we understand how to solve problems like this, then we can solve each of these for each of the i's coming from the prime factorization of n. Have all the solutions here, and then for each combination of solutions, taking one solution for each I, for each combination that you can put together, the Chinese remainder theorem will correspond this set of solutions unique to a unique congruence class modulo n, which will be one of the solutions of the original, one of the solutions. So the main kind of work in one of the big substantial pieces later on in chapter 7 is working out how to solve problems like this. But before solving these kinds of problems, fx congruent to 0 modulo ei to the ai, we want to understand the simplest case of it. F of x congruent to 0 modulo a prime p. It's just modulo a single prime. In general, we're going to have to be able to solve modulo a prime to some power, but the simplest case of that, initial case of that, would be this kind of thing. So this is what we're going to look at today. This is Theorem 7.1. Now, it doesn't quite tell you how to solve it or that, but it does give you information about the number of solutions. It gives us an upper bound on the number of possible solutions that this thing might have. You remember when we started talking about polynomial congruences, we mentioned the fundamental theorem of algebra about polynomial equation. Polynomial equation, degree n, n is the highest power of x in polynomial. Polynomial equation always has n complex solutions. And the solutions, their multiplicities. You always have n solutions. You always have the exact number of solutions corresponding to the degree of the polynomial. Now, you don't have such an exact relationship like that for polynomial congruences, but you kind of do. And it's expressed in Theorem 7.1. So 7.1, we're looking at this situation here, where f is a polynomial of degree n. So let's say f of x is the sum from I equals 0, n, ai, x to the power I. So this looks like a polynomial of degree n. Yeah, so x to the power 0, x to the power 1, x squared, x cubed, all the way up to x to the power n. It's got various coefficients. But if we're going to be considering a polynomial congruence modulo p, we want it to genuinely be of degree n. So we want to make sure that our leading coefficient, an, the coefficient of x to the power n, we've got to make sure that that's not congruent to 0 modulo p. Because then it isn't really a polynomial of degree n. If the leading coefficient was divisible by p, because then an times x to the power n, no matter what x is, it would always be congruent to 0 modulo p. So we have this to be considered a congruence of degree n. We need the fact that p must not divide an, so that it's genuinely of degree n. Or you can express that in terms of congruences. An is not congruent to 0 modulo. Congruent to 0 mod p is the same as p divides. So if that's the case, then this congruence star, the conclusion of the theorem, has at most n solutions. Not exactly n. Sometimes sometimes it might have n solutions, but sometimes it might have less solutions. Sometimes it might have no solutions at all. Okay, so it's not as good as the fundamental theorem of algebra, where it says it has exactly n solutions. It's a weakened form of that. So the degree of the polynomial, so this n is the degree of the polynomial, it gives us an upper bound on the number of solutions that the polynomial congruence will have. If you do, maybe next time, maybe tomorrow, you could look at some examples. But if you can get Sage or get the computer to just specify a polynomial, you can loop through loads of primes, get it to solve it, and you'll see you get various combinations. Like you put in a cubic, sometimes you have 3 solutions, sometimes you have 2 solutions, sometimes you have 1, sometimes you have none, various choices of prime p. But you can observe this. You compute some examples, you'll see that the degree of the polynomial is always an upper bound on the number of solutions.
You just say there can be no solutions.
Yeah, there can be no solutions as well. Yeah.
There are criteria to which you can say there will be, or
yeah. So that kind of So that's kind of something we'll be studying in chapter 8. Yeah. So you can certainly have quadratics that have no solutions.
that'd be good to
Some
say.
p. Yeah. Yeah. That's a whole kind of subject, and we link it to the discriminant. It's like our connections with the situation with polynomial equations. Yeah. Okay, so let's think about proving this. Now, it's quite a substantial result. It's not a quick proof or anything, but we will fit it in to the lecture. I think it's fully spelled out in the notes, but I just would like to kind of step through it and pick out the main points in it. We're going to prove it by induction. By induction on n, the degree of f. And inside the proof by induction, when we're doing the main induction step, there's a really nice proof by contradiction. So it's a nice substantial proof in that you see a fair number of techniques at play and interact. So we'll begin the induction at the base case of n equals 1. I mean, you can have degree 0 polynomials, but they're just constants, and then it's just that's not particularly interesting. I mean, if the constant is 0 mod p, then there's an infinite number of solutions. Any x will be a solution. If the constant isn't congruent to 0 mod p, no solution. So that's not really relevant. So I think we're talking about n being bigger than or equal to 1. N being bigger than or equal to 1. Well, actually, no. So let's choose the base case n equals 1. So there we're talking about, i.e., a polynomial congruence like this, where, and we've got this condition here where p does not divide a1. But now we've already dealt with these cases, okay? Because this was the subject of the previous chapter, linear congruences. And if the prime number does not divide this coefficient of x, that means, i.e., the GCD of a1 and p is 1, and so this has a unique solution. unique solution mod P. A unique solution, so i.e. one solution. So this polynomial of degree 1 has one solution. So the theorem is true. 1 is an upper bound on the number of solutions. Remember, the solution was x congruent to minus a1 inverse a0. The inverse exists. You can multiply both sides by the inverse. Bring this part over here, so you get x congruent to minus a1 inverse a0. So the theorem is true for n equals 1. Great. So our polynomial of degree 1 has exactly satisfying this non-divisibility thing on the leading coefficient, so it is genuinely of degree 1, and it has one solution. So that's the base case proved. So now we make the induction assumption. Yeah. So assume the theorem is true. For some k greater than or equal to 1. So let's just make clear what we're assuming there. So all polynomials, all polynomial congruences of degree k with p not dividing ak, the leading coefficient, because I'm using this notation up here, ak would be the leading coefficient of your f. All such polynomials here have at most k solutions. That's our assumption. And it's proof by induction. So now we're going to try and deduce the same thing for polynomials of degree k plus 1. So we have to show for all polynomials of degree k plus 1, where p does not divide the leading coefficient of it, that they have at most k plus 1 solutions. And let's prove the same for polys 3k plus 1. That's how our proof by induction works. But we're going to do this by contradiction. So we're going to use a proof by contradiction to prove the induction step. Everybody with the any clarification? We proved the base case, we made our induction assumption. This is the theorem quoted for polys of degree k. We're going to use this assumption to prove that it's true for polys of degree k plus 1. But this we're going to do by contradiction. So what does it mean? What does it mean to say that this statement in the blue box here is false for polynomials of degree k plus 1? So I'm going to do proof by contradiction. So I'm going to assume that the thing I'm trying to prove is false. Assume that this statement in the box for polys of degree k plus 1, I'm going to assume it's false. And the statement says all polys of a certain kind have at most k solutions. So that's going to be false. It means there is at least one polynomial of this kind that has too many solutions. The statement says there are at most this number of solutions. So if it's false, it must be that there's some bad polynomial around, at least one, which has too many solutions. Naughty polynomial. Okay. So if I'm doing my proof by contradiction, that's what when I assume the result I'm trying to prove is false, that's what I'm assuming. Assuming there's a bad polynomial. So assume there exists, so I call it there, I call it G. A poly G. Let's be specific about this. Let's write it down, give it a formula. We'll use B's for its coefficients. It's going to be of degree k plus 1. We're going to consider it modulo this prime where, and it must satisfy the criteria, so P does not divide B k plus 1. But it is a bad polynomial. It has too many solutions. Must violate this condition in the box for k plus 1. So k plus 1 is not an upper bound for the number of solutions. G has at least k plus 2 solutions. Let's denote those as x0, x1, x2, up as far as x k plus 1. Okay, so this is our bad polynomial. Trying to prove that no such things exist. I'm going to do it by contradictions. We assume a bad polynomial exists. Degree k plus 1, genuinely of degree k plus 1. The leading coefficient is not 0 mod p. And it has at least k plus 2 solutions.
And that's kind of that form, like holds for all solutions greater than k, that they don't exist. Because aren't we just putting an upper bound on saying, well, we're proving it by just saying that only the k plus 1 solution doesn't exist? How are we definitely capturing all solutions greater than k by putting the k plus 1 on the limit of the sum?
No, so just remember where we are. We're in the middle of the proof by induction.
Yeah.
So we proved the base. So the theorem is this statement in the blue box for all polynomials.
Yeah.
Not polynomials of a certain degree, but for all polynomials. That's what we're trying to prove. Okay. We proved the base case. We assume the theorem is true for some intermediate value. Basically, we assume that that's true. And now we're trying to deduce this statement, trying to deduce the theorem for polynomials of the next highest degree, of degree k plus 1.
How does that encapture solutions greater than k plus 1? How can we confidently say that there's no solutions that are greater than k plus 1, that they don't exist either?
Because it'll be the principle of induction that goes first.
Okay.
Yeah. Because the base case proves there's no bad polynomials of degree 1.
Yeah.
This linking step, when we achieve it, will prove there's no bad polynomials of degree 2.
Yeah.
Then the linking step shows there's no bad polynomials of degree 3. So
it just follows on. Yeah.
Induction then takes care of all the degrees.
Okay. Thank you.
Is that all right?
Yes.
Yeah. So we're doing induction on the degree of the polynomial. And in that way, we'll sweep through all polynomials. Because any polynomial has a certain degree. So if we sweep through all the possible degrees, we will be sweeping through all the polynomials. Okay. Now it is. You do have to digest this carefully. It's not a simple like one-page induction proof that we've done at the start of the year, whereas like the argument fits on a few lines. It's a substantial argument. Okay? So we made the assumption, and now we've just articulated. Now we're trying to prove this assumption for k plus 1, or we're going to prove it by contradiction. So we assume the statement for k plus 1 is false. It is not true that every polynomial has at most k plus 1 solutions when the polynomial is degree k plus 1. So that means we can grab a hold of a bad polynomial. We're assuming falsely, which we'll see when we get the contradiction out of it. We're assuming that there exists a bad polynomial which has degree k plus 1, and it has too many solutions. It has at least k plus 2 solutions. Starting counting at 0, so 0 to k plus 1 is k plus 2 solutions. So it's from this, from the existence of this polynomial, little g, I want to derive a contradiction. This is the bad g. It shouldn't exist, and we're going to prove it can't exist by showing that it leads to a contradiction. Now, the thing it's going to contradict is this statement in the blue box that we just assumed. Okay? And that will show that the statement in the blue box implies there does not exist any bad polynomial. We're going to show the existence of a bad polynomial implies that this statement here is false. Contrapositive of that, which we want, is the induction step, that this statement in the blue box implies there are no bad polynomials. Now, consider a related polynomial, capital G. So we're going to define a related polynomial, and it's the little polynomial, it's a polynomial little g minus a particular constant. So we're going to subtract the value little g of x naught. So x naught is the first of our solutions to g of x, and we're going to subtract it from g of x. So we can write out what this polynomial looks like. It's got, so the coefficients of little g are b, bi. We got the polynomial g, so that's x to the power I. But then you're subtracting the x naught. And g of x naught is the sum of bi times x naught to the I. So you're subtracting all these powers of x naught. Each of them is multiplied by bi, so you can kind of factor it out. And we're summing over the values. Well, we can actually begin this sum at 1, going up to k plus 1. I don't have to do it, because when you're looking at I equals 0, when I equals 0, you've got x to the power naught, which is 1, x naught to the power naught, which is 1. So you've actually just got 0 in this bracket too. So, I mean, you could do this sum starting at 0, but there's just a 0 there anyway. So I may as well start that. May as well start that one. Now you may see already. What we're going to do is we're going to factorize this capital G. All these terms. Remember, when you do a difference of powers, you can always factor out x minus x naught out of each of those. Okay, so we can always do a factorization like that. So notice that g of x naught is actually equal to 0. Yeah, capital G of x naught is little g of x naught minus little g of x naught. So that's just 0. So x naught is a root of the equation g of x equals 0. So this is a factor of the poly capital G. So we can factorize it. Factorize it as capital G of x is going to be x minus x naught into some polynomial h of x. And it's this polynomial h of x which is very suspect. And we're going to interrogate h of x. So we can factorize it as this, where h of x is a polynomial integer coefficients. G is factorizing out x minus x naught. Now, someone tell me what the degree of h is.
Just 1 less than 2.
Yeah, so which is k, yeah. So the degree of h is k. That means it's covered by the induction assumption we made, or it's potentially covered by the induction assumption we made, because the induction assumption refers to all polynomials of degree k. So this h is degree k. H has leading coefficients. What's the leading coefficient of h? What's the coefficient of the high of x to the power k within h? So h has to have degree k because capital G is degree k plus 1, and you're multiplying it by this factor x minus something. So this has to be degree k in order, so if you multiply it by x, you get something of degree k plus 1. But what's the coefficient of x to the power k within h? Well, the leading coefficient of capital G is the coefficient of x to the power k plus 1. And the coefficient of x to the power k plus 1 in capital G is bk plus 1. Yeah. The leading coefficient in capital G is bk plus 1. So that means, but the k plus 1 term here, when you multiply this out, you have x times the k plus 1, the x to the power k term here. That gives you the k plus 1 term here. So the coefficient of x to the power k in here must be the same number bk plus 1. So when you multiply it by an x, you get bk plus 1 times x to the k plus 1. That comes from the factorization. So the leading coefficient is bk plus 1. Yeah. I.e. h of x, whatever h of x looks like, it's b k plus 1 x to the k plus other lower degree terms. But h of x it's a polynomial of degree k. And up here we already know that p does not divide b to the k plus 1. That comes from above. So what we've done here i.e. h is a polynomial covered by the induction assumption. So the induction assumption would say that this has at most k solutions. But we're going to see now, shortly, that h has, in fact, at least k plus 1 solutions. H has too many solutions. Can't have too many solutions because of the induction assumption, we assume that all polynomials of degree k obey the theorem. This polynomial h, we're going to see, does not obey the theorem. So note that for all values of j between 1 and k plus 1, when you look at capital X, capital G of xj, this is g of xj minus g of x naught, remember? That's how capital G is defined. And this, remember, is equal to, well, capital G we now have factorized. So xj minus x naught times h of xj. But these two, or they're both the same thing. This is congruent to 0 mod p. Why is it congruent to 0 mod p? Well, the xj and the x0, they're both solutions to the polynomial congruence little g congruent to 0. So when you're subtracting two things that are congruent to 0 mod p, it's still congruent to 0 mod p. So that implies, i.e., if you look at the definition of congruence, it means p divides xj minus x0 times h of xj. That's what being congruent to 0 mod p means. Again, this comes back to you. What are you thinking when you see a statement that p divides a product of two numbers? That must immediately trigger something in your minds.
One of them must be divisible by p.
Yeah, one of them must be divisible by p. This is the quintessential feature of prime numbers. Some people see it as the definition of a prime number. Prime numbers are those numbers that have this property that whenever you know that p divides a product, it must be the case that p divides at least one of the factors. Can't split p up. It's unfactorizable, so it must be wholly contained in one of these two numbers. But we know that p does not divide this. Why do we know this? Because when you look at, these are differences between one of the xj's, and that could be x1 up to xk plus 1, and the difference between that and x0. But you see, these were introduced as distinct solutions, mod p. So that means each of these x's here are all distinct modulo p. So that means p never divides a difference between them, because that would mean that they were congruent. We know p does not divide xj minus x0. So let's just emphasize that up here. G has at least k plus 2 solutions. So these things are all distinct mod p. So where we introduce the solutions xi, they're all distinct modulo p. Well, if they're all distinct modulo p, it means their differences are not divisible by p. So p must divide this product, but we know it doesn't divide this term, therefore we know it must divide the h value. That implies that p does divide h of xj. i.e., oh, sorry, yeah. Does divide, I hate h of xj. Does divide. So h of xj, in other words, is congruent to 0 mod p. So each xj is a solution of h. And what are the options for j? The option is 1 to k plus 1. So h has at least k plus 1 solutions. That looks very troubling because further up the page, when we began the induction part of the proof, we assumed that every polynomial of degree k with leading coefficient not divisible by p had at most k solutions. But here suddenly we've got in front of us such a polynomial h, which has at least k plus 1 solutions. It has too many solutions. So this contradicts the induction assumption. I want to give this a nice label. I think I called something star already, so I'm going to call this star. Induction assumption in the big blue box. So the existence of this h contradicts star. Now, you have to stand back and look at the logic of what we've shown. We showed that if we assumed there was a bad polynomial at degree k plus 1 level, all this argument leading about this h is all perfectly fine, flowing from this assumption that there exists this little g. So if there exists a bad polynomial at degree k plus 1, we've shown that there must exist a bad polynomial at degree k. So that means if all polynomials at degree k are good, that implies all polynomials at degree k plus 1 are also good. Existence of a bad polynomial at degree k plus 1 implies existence of a bad polynomial at degree k. So the contrapositive of that, if all polynomials at degree k are good, but don't have too many solutions, then all polynomials at degree level k plus 1 must also be. So that's the completion of the proof of the induction step. So H contradicts star star. Well, where did H come from? H came from factorizing capital G. Here. H came from factorizing capital G. Where did capital G come from? Capital G came from the polynomial little g. So little g, in effect, contradicts, existence of little g contradicts the assumption star star. So little g cannot exist if the assumption star star is true. Assumption star star implies there are no bad polynomials at degree level k plus 1. Hence, so does the existence of little g contradict star star. So star star implies the theorem is true for polys of degree k plus 1. So by the principle of induction, it must therefore be true for polynomials of all degrees. So in effect, all polynomials. By induction, theorem is true for all polynomials. Very interesting, right in there. What did we call that? We call that that was Euclid's lemma, wasn't it? Back in chapter 3. Prime numbers. Euclid's lemma. So it's a really good example of a nice substantial proof. It's a proof by induction, but not doing induction over the kind of direct subject of the statement. The subject of the statement is polynomials, but we're doing induction over the degree of the polynomials. So we prove directly it's true for the base case of all polynomials of degree 1. That was covered in last week, chapter 6. We then assume it's true for all polynomials of a certain intermediate degree k, and then by a careful argument, by proof by contradiction, we show that this assumption implies there are no bad, that it's also true for all polynomials of degree k plus 1. So by induction, then it's true for polynomials of all degrees, so that means all polynomials. So that gives us a very secure starting point, where we know that for a polynomial congruence of degree of polynomial congruence modulo prime, we've got a strict upper bound on the number of solutions from the degree of the polynomial. So it gives us a secure footing from where to start. Okay. So tomorrow we'll talk about how we kind of continue in our journey to be able to solve a general polynomial complex, modulo general modulus. Okay, so see you then.